Hi, Joanta. Hi, Tao.
How are you?
Oh, doing good, doing good. Thank you.
Great, great. Just to learn how you kind of teaching such kind of class. I probably will teach a similar class in the next spring semester. So also need to learn from you.
Yeah.
I'm not sure. I think let's see. Is the lead is coming
He was here on Monday. I don't know.
Monday? Okay.
I don't know. Maybe I did scare him away.
No. I don't think so. I haven't talked to him yet, but I think he is eager to learn something. Yeah.
Well, maybe he decided that it is too easy for him.
I hope not. So this class will last for like a month or 2 months.
For month and until the end of the. Well, I think the end of summer semester is like August
Oh,
15th.
okay, that's good. That's good.
But the semester is shorter than regular one, so I right now I am not doing any updates. I'm just using materials from regular semester, but I soon I will need to squeeze and maybe put two logical lectures into one physical lecture.
That's good. Yeah.
Maybe you can wait some time. The students will join.
Yep. I have no doubts that someone, few more will join.
Yeah, you are right.
So Jayanta, how are you doing?
Yeah, fine.
Did
How
you?
are you?
Oh, doing good. Thanks for asking.
Yeah,
Did you try to do some homeworks?
I will try because last couple of days I was not very well.
Uh huh.
That's why.
Oh, I wish you feel good, and please consider to um, invest time in picking up
Yeah,
materials
yeah.
now. Uh-huh.
I'll invest.
Before it will be too late. So that
Yeah.
okay.
I will try my best.
Okay, thank you.
Yeah, you are welcome.
Oh, hi you. Nice seeing you connected. Okay, so we have three participants. It's it's good.
I think Mahima will come later. Jenish maybe will come later. Christian.
I hope they will.
Yeah.
Okay, I suggest we start now, and I believe our meetings is recorded, so it should be it should be good for to share to those who join later. So if you are not speaking at the time, please consider to mute the microphone and unmute it when answering questions or asking your own question. I just hear a little bit of feedback. J- Jayanta,
Yeah.
would you consider to mute the microphone when you're not
Yeah.
speaking?
Thanks.
Okay, very good. Um, Okay. So we are in the summer version of the computational chemistry course, and the goal of the course is to pink box to get over some background theories, but since it is mostly practical course, we just need to pick up some terminology and main logical connection, and then apply theories be to get hands on for using right software on the right hardware. Oh, hi Kristen, nice seeing you connected. And the ultimate goal is to assist research programs of all participants to compute some observables for computational characterization of materials and compare them to experiment. So first, the goal is that I spend only 30 minutes for theory background, and then most of the remaining time we do practical exercises, but sometimes it gets a little longer. So here is approximate schematic diagram for the organization of the course. So there are 4 chapters, and we have finished the first chapter on molecular modeling and geometry optimization. And now we are in the second chapter for very basic approach to electronic structure, Hartree-Fock theory. And for today's meeting, we will try to focus on variational theorem and combination of atomic orbitals to form molecular orbitals. The in about 3 meetings from now, there will be presentations of participants of the course. So the subjects displayed here needs to be presented, and if you have already signed up to one of the boxes, it's great. If you didn't, like Joanta, please consider which subject you want to present, and
which of the things are remaining?
so you see, Dr. Yu has signed up for box number 2, how to prepare GeoN9 input. Kristen has signed up for this red box. Mahima, by now, she has signed up for symmetry groups, but I will ask her to present something more. Janice wants to do molecular orbitals, and now we have remaining the first box, available electronic structure and other things. It's quite easy. And the last one, Millikan charge analysis. So you may select, but number 1 is doesn't require any background. You can start from scratch, and it's a good option.
Okay, I'll try first one.
Okay, and please, I do not want to put my words into your mouth, so to say. So there is a link. Let me share it with everyone. There is a link for Google Docs, so you may redecide and or confirm your decision and type your name near this. Let me bring up. I will bring it in a second. Sign up. So there is a Google Docs document with no, like this one. Google Docs document right here, and if you want, you can type your name. Well, I can put it here, but you have privileges to modify and move your name to any other subjects.
Okay.
Okay.
I think, Professor Dimitri, you can wait some time.
Yes.
I think Janice and Mahima can come.
Yeah, this is very good, but maybe they will come at the time I will be presenting new materials. Right now, I'm doing reviews which are not as not as critically important. So, also, do we have Lihu? No, but if he will continue to attend the meetings, he may also pick up some material to present. Okay, so let me copy this version to our slides, and it's fine to keep updating these materials as we go. So today, after I finish mumbling about theories, we will focus on the magenta box. So we will analyze output of Gaussian file in graphical form. So we will pick up the concept of so-called density of states. Okay, so I have gianted for the subject number one. Also, I'm very relaxed with homeworks, and the presentations provide the maximal contribution to the grades. But if you want to practice, it is very recommended, and there is a reward in points for homeworks. So here is something for coming Monday. So the the steps from A to D seems to be completed for those who were doing the previous homework. So consider the progression of the titanium hydroxide oligomers and run the Hartree-Fock calculation and extract HOMO-LUMO gap, total energy. The example is in lower right. For the next homework, please try to create one slide explaining what is Koopman's theorem. It's quite easy. And another thing, to go over all models that you are exploring in the course and make your best attempt to plot so-called DOS, density of states. So we will go over the concept of density of states on today's lab, and then please try to apply it to this titanium hydroxide models, to this silicon and diazonium, and to carbon nanotube. Okay, so when we were doing the last lab, or even second last, I would say 10, 12, we were running the models, operating them with Gauss-Hughes software, and selecting single point method basis set, and then in the output which sets up the input, and then in the output we were getting a list of orbitals, a list of molecular orbitals and their energies, occupied and unoccupied, and most important things are last occupied and first unoccupied, and it is what those of you who were doing homeworks reported in this homework. When I will finish overview of some theories, we will go to next practical step of converting this list of orbitals into a form that which is much more pleasant and easy to analyze for human eye. So even for this ridiculously small model with 9 atoms, you see that there are like around 50 states, and for human brain it is not natural to follow all of them. But there is a concept that converts energies of all molecular orbitals in one continuous graph that can be analyzed in a fraction of a second, and is a it is called density of states. So I will talk about it more as we go. And today we will go over practical steps over extracting the list of orbitals from the density of states. So if you this slide and next slide, 17 and 18, are most important for the today's lab. So you may want even to copy paste them and keep them somewhere when we will be doing practical steps. So basically we will be copying these lines and implementing them and practicing them. So I will go over them carefully line by line, and the end goal of today's meeting is to get the image like the one at the bottom of the slide. So the meaning of this image is that we do have occupied and unoccupied orbitals all collected together in graphical form. And this figure, this style of figure, will remain the same independent of how many atoms and how many orbitals are available in the given model. So it's quite universal. So if you don't care about equations, you can mute the speaker, lean back and relax for another 20-30 minutes. So there will be a boring part, and the main goal is to pick up terminology and logical connections for the theories behind the software that we are running. So in previous couple of lectures, we were going over logical steps towards Hartree-Fock theory. The goal of the theory is to assume that positions of nuclei are nailed to fixed points, and we are looking only for eigenstates of electrons. We are solving electronic problem. The main challenge is that there are so many electrons, and the wave function that depends on many electrons is not possible to treat with today's computers. And we are going over several background concepts. So concept of Slater determinant that is originating from description of multi-spin problem. Then last time we covered mean field theory, and today we are going to cover so-called variational theorem. So after we come over all of these logical steps, we will see the flow chart, how Hartree-Fock theory is working, and where these orbitals are coming from, and where the total energy is coming from, and why one believes that approximately one can partially believe the results of Hartree-Fock theory. So here is the equation that we are solving. So Schrödinger equation for wave function that depends on positions of all electrons. So electron number 1 up to electron number n. And we believe that one function of many variables can be represented as many functions of one variable with anti-symmetrization procedure, so expressed as Slater determinant. And last meeting, we were considering the mean field theory. So if we take a molecule, remove all electrons, and then return them, throw them back into the molecule, first electron will try to navigate to spots near attractive positive ions. Second electron will be screened, repelled off from the sweet spots by the first electron, which is already negative. So and each next electron will feel the repulsive force of the electrons that are already settled in the molecule. And the concept of this mean field combined from attraction by nucleus and repulsion from the rest of electrons is one of the cornerstones of Hartree-Fock theory. Then we did try to implement this idea into the form of mathematical expressions with some simplifications. So we did play the wheel of fortune and agreed that there is a procedure which is called expectation value, which helps to extract observable out of wave function. So if you have wave function and wave function conjugated, and we convolute it with operator of an observable, then from operator and wave function, one is getting a number. But if our wave function is a combination, is a product of several one-electronic wave functions, we can do a trick. We can do partial expectation value computation. So, and it is the last slide from last lecture. So if our wave function is a product of wave function 1 for electron 1 and wave function 2 for electron 2, one can practice partial convolution of the Hamiltonian operator.
So Dimitri, one question.
Oh, please.
All the time for electronic wave function, we have to write in only Kate form.
Please repeat.
Last here you have written like phi is equal to psi 1 Kate, psi 2 Kate. All the time Kate means like column matrix.
Yes, cat is column and bra is row. Yes. The bra and cat notations are applied as a way to practice laziness, at least for me and maybe for you as well. So if we use bra and cat notation, then we do not write integration. Like if you write bra operator cat, then we skip writing the explicit integration. And if we by some reason, if I hate bra and cat, I need to rewrite it as integral over all independent variables, and they can be more than one. So dr1, then as many integrals as many independent variables, integral dr sub n, and then I'm writing phi star, and then if I'm not lazy, I need to put brackets and list all arguments, then operator, and then phi without star and also with all arguments. And the bra and cat notations seems just shorter, like abbreviation.
Means all the time, like integration means total summation.
You can say so. Integrate, yeah. So if and what we are doing now, we are doing it superficially and quickly without details, but it is way above standard physical chemistry and standard quantum mechanics. So we are considering multi-electron problems, which are really challenging. And now on this slide, last slide from last lecture, we are trying to convert multi-electron problem into one electron problem. So,
great.
So here we want to set up an equation for the first electron, and
okay.
And here there is a expectation value of electronic Hamiltonian in respect to the second electron.
Okay.
So we did partial convolution, partial expectation value procedure. So in respect to second electron, it is already a number, but in respect to the first electron, it's still an operator. And then we can do the same procedure for like second electron. Now this lower line is an equation for second electron, and the thing in the big brackets is the expectation value of Hamiltonian in respect to the first electron. So,
thank you.
Thank you for asking, Joanta. So we are moving from, and here this example shows moving from 2 electron problem to 1 electron problem, but if you have more than 2, the principle is the same. And by, yes?
What is the repulsion?
Repulsion, electrons repel each other because they have the same sign, and they repel each other. The stronger, the closer they are to each other. Right?
Thanks.
Okay. And with this, we are finished in reviewing the previous meeting. And we are starting today's meeting. So if you will try to look into textbooks or Wikipedia for variational principle, it will be so brief, so short, that it's very often one reads through and forgets that it has been read. So it's just a couple of lines. So I will try to expand a couple of lines in a textbook in the like whole in the more detailed discussion. So the variational principle itself would replace all equations and all quantum chemistry if you would have infinitely powerful computers. So if we all have accepted our game of Wheel of Fortune when we were guessing this word, expectation value, if we accept the concept of expectation values, and if we can randomly generate a wave function, randomly generate multi-electron wave function, then take bra and ket of it, conjugate and not conjugate, and find expectation value of Hamiltonian. Then we will get total energy, right? Oh, I do see someone is having a comment. Let me check. Maybe it's something important. Joantis, thanks for a nice explanation. Thank you for a very appropriate question. So, if we do have a procedure of generating random wave functions, and we have procedure to construct total energy out of random wave functions, which is just finding expectation value with bra and ket, then here I'm offering a crazy, fantastic idea, of doing all calculations without actual Schrödinger equation. So only having operator and random wave function. So we use random number generator to fabricate random wave function. Find total energy through expectation value procedure and save it into a very powerful disk space. Then we repeat this procedure, generate random wave function once again, find with Brian Cat the expectation value and save it into the powerful disk drive and repeat it again many times. Then we are going through the list of total energies, arrange them in the descending order, and selecting the smallest of them. So selecting the smallest expectation value of total energy. And then find, oh, okay, for this smallest value of total energy, it did originate from this random wave function. And then we declare, okay, this random wave function is absolute truth. It is what would correspond to a nature. This seems like quite quick idea, but with modern computer power, it may take much longer than any of our efforts. But what we learn from it is that knowledge of expectation value out of wave function is a path to find the minimal total energy. So the wave function that gives minimal total energy is the correct one. Okay. So here are the bra and cat notations that I appreciate question of Jayanta. So we have a wave function, electronic Hamiltonian, and just in case, if wave functions by some reason were not normalized, we can divide them by normalization factor. So
okay.
Suppose we did found ideal wave function that corresponds to the nature and reproduce minimal total energy of the best electronic configuration of a molecule.
Okay.
Now we may hypothetically try to add some additional random term to this wave function, this delta psi.
Okay.
I'm hearing your breeze, but I know this is more philosophical concepts, but later on they will help for beautiful theory that we are already using hard to focus. And here is just a little cartoon. So if this ideal wave function is, let's say, like Gaussian, maybe multidimensional, and this delta psi is a little additions on the shoulders, then adding them together will be like Gaussian with two shoulders.
Okay.
If you have one dimension. Now,
suppose if
yes?
I want to transfer it like 2 dimension or 3 dimension, then I have to add it like del psi 1, del psi 2, del psi 3.
No. This psi and delta psi are multidimensional. Just all humans have their strengths and weakness in comparison to computers, and my weakness as a human that I cannot draw 4-dimensional, 5-dimensional images. But the concept.
Suppose
yes.
Just one question. Let me
please.
Tell
please.
question. Suppose if I want to transfer 3 dimension, so what will be the small changes? That will be CHEM or that will be different?
So right now we are describing abstract, not practical idea. So small meaning the heights of this peak, the area under these peaks is much smaller than area under this peak.
Okay.
So the area under main wave function and area under the small increment are of different order of magnitude. And now here is the theorem. So if our psi naught is a wave function that gives absolutely correct total energy on the left side. And on the right side, we will try to find total energy of the wave function that with these side peaks.
Okay.
So the total energy of the wave function with side peaks will be always bigger than the total energy of the ideal wave function.
That you are definitely, because you are adding del psi means that should be greater than previous one.
Yes, yes. Well, this
adding energy.
This delta can be negative, but it can be even complex. The theorem is that any change to ideal wave function will increase total energy.
So if you are telling like that del psi, if del psi will be negative, then left side should be greater than right side.
Right side will be always bigger than the left side.
No, you are telling now that if del psi will be negative, then the total addition, psi 0 plus minus of del psi, h, psi 0 plus minus of del psi, h. So the left side would be greater, or all the time right side would be greater?
Suppose we have minus sign here instead of plus. So even if we have minus sign instead of plus, the inequality will be the same.
Okay, means you are taking mod.
So no matter how you change your ideal wave function, any change to ideal wave function will lead to increase of the total energy.
Okay.
Okay, and it seems quite natural, and later on we will use this theorem as a building block to both Hartree-Fock theory and later to the DFT, which is a workhorse of modern material science. So basically, by now, all of us know what is variational theorem is. And now I will bring a couple of side concepts, because we are building big theory through like a couple of weeks effort. So I am going to lead the discussion for connecting together several concepts. So when the atoms are very far from each other, like if you take a molecule, break all branes and put atoms far away from each other, then it will be electrons on these atoms will take atomic orbitals. If you bring atoms composing a molecule close to the realistic interatomic distances, electrons will take molecular orbitals. But molecular orbitals can be expressed in terms of atomic orbitals. So it's one concept. Another one, if you have many atomic orbitals, but each of them is a function of one electron, then we need a procedure of how to combine molecular orbitals of one electron into wave function of the overall molecule, which is multi-electron wave function. So we have like several layers.
So what is the basic difference of multi-electron wave function and suppose 3 or 4 electron or maybe 5 electron wave function? Maybe 1 electron wave function. What is the difference? Total, suppose n is equal to 100, n is equal to 1, or n is equal to 3.
So the wave function of overall molecule has as many independent arguments as many electrons in this molecule. Like if it is molecular hydrogen, it is 2 electrons. If it is acetylene, it will be how many? 6 electrons from each carbon. right?
Mm-hmm.
12 plus 2, 14 electrons. And then as we go to bigger and bigger examples, wave functions will be a function of large number of electrons. But molecular orbitals, even in complicated molecules, are always a function of one electron. And we set this hierarchy. So lowest order is atomic orbital, next level is molecular orbital, and highest order is overall wave function, which is multi-electron object.
Okay.
Okay?
Thanks.
Oh, my pleasure, my pleasure.
Yeah, you're welcome.
So, and here, let me introduce notations. And again, if you do not follow all of this, do not worry. Our main thing are practical exercises that we will do very soon. But those notations and connections between them are just auxiliary. So suppose we have the atom number I centered at position R capital. And then we have atomic orbital as function of position of electron that is rotating, moving around this ion. So it is position of electron minus position of ion. And for atomic orbital, we will use symbol chi, Greek chi, which looks like Latin X. And the index A, I probably can go to the next slide because it was already written here. So index A corresponds to all quantum numbers for atomic orbitals, like for hydrogen atom. So principal, orbital, magnetic, and spin. I just, for being lazy, I combine all of them in one super index A. Now, so this is the lowest level, atomic orbital. Now, if we have so many ions with upper case I, on each ion we have atomic orbitals, and we can count them by running through different values of these atomic indices. And then we have weight, we have contribution percentage. So each of the atomic orbital sitting on each ion gives so many percent to a molecular orbital number J, so to say. So this expansion is a pathway from lowest level to mid level, how to go from atomic orbitals to molecular orbital. Okay? If anyone has objections or questions, please bring them up. Okay, I think no one objects. It's a good sign in this case. And here is the hierarchy. So we are, this brief line that I'm going to show is very natural. We all understand it with intuitive feeling, but I'm trying to bring in a little certainty and notation. So we start our computations with setting up positions of each ion. So this uppercase R sub I. And then after playing with this black box, or here it is red box, we are getting total energy. So the main goal of any electronic structure theory is to get total energy. So we start from positions of atoms and we get total energy. And inside this black box, we have the several objects. So atomic orbitals, chi, then expansion coefficients that can give contributions of atomic orbitals and form molecular orbitals. And then we combine molecular orbitals into wave function of the whole molecule, which has which is a many electron wave function. So if you already got some practice in Gaussian and Gauss view, and I believe you did because we were doing it together 2 days ago. So when we are writing Gaussian, these coefficients of expansion of molecular orbitals over atomic orbitals, C with indices A and J, they are saved in check, CHK, and form check files. Then when we practice the command in the command line cube gen, we do nothing but combination of atomic orbitals and expansion coefficients and generate molecular orbitals. And we get this .cube files. So when we were plotting orbitals in our previous lab, we were practicing conversion of these expansion coefficients into cube files, into molecular orbitals. And now I want to offer a question that I will answer myself, but maybe we can discuss it. So in our path from positions of ions to total energy, which of these intermediate concepts we are allowed to modify and improve? Are they all because we want to improve something, improve shape of wave function, orbitals, something inside, in order to get minimal total energy. So which of these four concepts we are allowed to modify? So please think, and I will either type or spell out the answer. Kristen, do you think we can change atomic orbitals? And if anyone wants to speak, do not hesitate.
Actually, the question is that could you please repeat the question again?
Okay. So we do want to do calculations which targets to find total energy. And on this path, we are going along these lines from atomic positions, which we are not changing if we are not optimizing geometry, right? So we can and then at the end we arrive to the total energy. So which of these objects we are allowed to change, not as users, but if suppose that we are writing a code for this theory, which parameters, which objects are modifiable and which are strong as stone?
Like you can change coefficient.
Exactly. Thank you so much. Yes. So atomic orbitals, they were solved by Schrödinger in 1927, and they are not changing, right?
They will not be changed.
No, but coefficients, the percent, yes, exactly, percentage with which atomic orbitals come into molecular orbitals are modifiable. So we can modify this C expansion coefficients. Yeah. Thank you for answering for everyone. So if we go over the list, then expansion coefficients is the only thing that can be changed. And in some sense, I'm going to oversimplify, but in some sense, Hartree-Fock theory is browsing in the space of expansion coefficients. So the task is to find such set of expansion coefficients which will give the minimal total energy. It is a little bit of exaggeration, but there is some rational in it. Okay, there is nothing useful in these slides. Well, the no. I want to bring one more little concept, and we will be done with this boring theories very soon.
Yeah, great.
Yes. So why we accept this later determinant form of combining molecular orbitals into total wave function? And I do have an answer. Because they include Pauli exclusion principle, because they include antisymmetry, right? If you want to object, please do. Okay. And now I want to illustrate what are the positive consequences of the use of Slater determinant of going from molecular orbitals to total energy. Let me summarize so that you do not lose interest and focus if you're following. The value of this antisymmetric form of Slater determinant that it will bring additional negative energy to the total energy, additional term with negative energy. And negative energy means attraction, means stabilization. So due to this antisymmetry, molecules will be more stable in calculation. So if one would neglect Slater determinant and just use product of one electron orbitals and do calculations, then most of the molecules will be predicted to be immediately decomposable. It will be explosive.
I have a question.
Please do.
Due to antisymmetric molecule will be stabilized?
Yes. In calculations, we like scientists try to understand nature, right? The actual molecules, they are what they are. But if we would try to model molecules without concept of antisymmetry, our calculations would give wrong prediction. That most of molecules.
One question. Suppose if you can think hydrogen 1 is orbital, and if you think that hydrogen 1 is orbital anti-symmetric mode, that will be stabilized more, or symmetric mode will be stabilized more?
Wait.
Definitely symmetric mode.
Wait, Joanta, the antisymmetry is applied only when there are more than one electron.
Oh, maybe you are talking about that helium.
Yes.
Or maybe hydrogen molecule, H2.
Yes. So the potential energy surface between two hydrogen atoms, if one would, it has a minimum, right? For interatomic distance.
That would be symmetric.
Wait. The potential energy surface depends on electronic structure. And if we recompute electronic structure without antisymmetry, the depth of this minimum will be much less. And in some molecules, it will just disappear. So the potential will be dissociative for a lot of molecules.
Oh, okay.
Okay. And I'm going to support this statement with a couple of illustrative equations. And then we will be done with equations and go to practical thing. So, when I was preparing these slides in the past, I was first time teaching it in the state of South Dakota, and when I was showing this equation, people were, "Oh, it's a slide about South Dakota." No, it is about Slater determinant. So, here we will go through these things very quick. Please do not be do not fear of a lots of equations. We do not need to solve anything. I will be just illustrating. So in here, I do have bra and ket. So bra is everything before this Coulomb term, ket is after. And to symbolize that it is bra, I put these stars everywhere. And as we discussed with Joanta, if we neglect this bra and ket notations, we need to put this explicit integration. Now, in this underline bracket, we do have Slater determinant for 2 orbitals and 2 electrons. So in the first term, we have first electron in orbital 1, second electron in orbital 2, and then first electron in orbital 2, and second electron in orbital 1, and minus sign between them. And in the ket, we do have the same ordering, just we do not have stars. In between, instead of placing the whole Hamiltonian, I put the most challenging part, the electron-electron interaction, 1 divided by R1 minus R2. So this is a procedure to get energy out of overall multi-electronic wave function. And in order to prove the statement about stabilization, I'm going to open brackets before this Coulombic operator and after this Coulombic operator. So before we have 2 terms, after we have 2 terms, so total number of terms should be 2 times 2, 4, right? And first, I will go the, just a second, I'll probably change a color. So while opening brackets, first I will take initial term from the bra and initial term from the ket. So when I go to the next slide, you'll see these 3 circles combined together. So first circle, last circle, middle circle. And we have number of electron and number of wave function coincide here, and they coincide there. So electrons do repel each other. Therefore, the sign in front of Coulombic term is plus. So this contribution to total energy will bring positive value. So this term, first term. And it is not surprising. 2 electrons repel each other. Positive energy means that they have force that drive them away from each other. Now, it's just maybe 1 or 2 minutes more, but it will be a little discovery. Let's go back to the original slide. And now I'm going to show the first circle, operator, and then...
What is SD here? SD?
Pardon me, just repeat.
What is SD here? SD.
SD stands for Slater determinant. So Slater. So it's name of a person, John Slater. He was working at different universities, and while retired, he was in Gainesville, Florida. So this combination of molecular orbitals with antisymmetry, with minus, comes from finding determinant of a symbolic matrix, and it is very important that we have a minus here. So now I'm going to take the first circle in bra operator and then last circle in ket. So keeping opening brackets. So first circle, last circle from cat, and the operator. So now we do have different order of operators. So in before operator is 1, 1, 2, 2, and here is 1, 2, 2, 1. So first electron in second orbital, second electron in first orbital. And due to discovery of Professor John Slater, in this term, we do have negative sign. So it is due to Pauli exclusion principle, due to Slater determinant, we do have negative sign in the Coulombic term. So, and it is very counterintuitive. We expect that Coulomb interaction between electrons of the same sign leads to repulsion, leads to positive contribution to energy. But due to Slater determinal, we have a term with negative sign. That there is a mechanism in the way how nature is arranged, so that there is a mechanism that for attractive, for stabilizing interaction between electrons of the same sign, charges of the same sign. And this stabilization mechanism later on becomes responsible for correct prediction of the molecules being stable in calculation. So we do not affect true nature. True nature, it is what it is. But in calculation, if we neglect this negative sign, the second term, this Slater determinant, then our calculations will be garbage. They will predict that most of molecules are unstable and will decompose. But with this term, we get much more correct results. Make sense?
Yeah.
Okay. And I think it is enough for lecture materials. I think those couple of slides are just verbal explanation what I just told. So negative term, and the correct word for this interaction is exchange interaction. So exchange interaction between electrons stabilizes molecules. Okay, enough for lecture materials. I will happily answer any questions, and I'm going to bring back the window with terminal window, and we are going to do some practical exercise. So I suggest that each of us will have is it large enough for the font? So if the font is not big enough, let me know. And I suggest that you have please use MOBA Xterm if you are a user of Windows PC, or Terminal if you are using Mac. For today's exercise, we do not need, we may survive without graphical connection. The things will be done all in command line, and the graphics will be just downloaded. Kristen, is it good enough, or should I make it even bigger? Just type if you want it bigger. If it is enough, then okay, good. So I suggest you have two windows open, one for the one on the Photon server, and another is on your local computer. And if you are coming for the first time, I can send the, well, if you do have your own facility, you can do the same things there. And if you want to do it on the NDSU facilities, let me share command. And if you need a keyword, please send it a request as an email so that we do not show keywords in this recorded stuff. Okay, so I'm typing the command, typing the keyword, and going to directory where we have enough space. And I'm going to the subdirectory for myself, and you please go into the directory where your exercises are stored. So make directory lab 12, and I do need from the previous exercise. I will show demonstration on the titanium hydroxide, titanium OH4, and the only thing that I need from last time is the .log file. So I can copy it from previous lab to here. Let me email to, or maybe I can just show it here. No, email will be better. Let me email the file with steps. So I'm going to, Joyanta, I just bought a new MacBook Air. Congratulations! From next week I will do it. You might try now on. Do you know how to? I'm not rushing you, but do you know how to, Joyanta? Do you know how to open terminal?
No.
Okay. Let me do a quick. Maybe I will do a quick demonstration right away, so that you follow all of us. So if you go to applications on the, you know where is applications panel?
No.
I'll show it, and I think I'll send the instructions to everyone that you can start practicing it even without me demonstrating it, and then I'll quickly help Joyanta. Okay. Apply to all. And I will attach this. You can see it in the slides that I just shared, but the standalone Word or PDF with only instructions for the lab will be, I think, will be more pleasant and useful. So in regular classes, we had only one lab per week, so instead of 12. It is. It was lab number 6. Choose instructions on books. Okay. And I Okay, I'm going to stop and and start screen sharing once again, just to make little demonstration for Jayanta. Jayanta?
Yeah.
Do you see my screen with Mac front panel?
Yeah.
So in the lower right, near the trash can, there is a folder with letter A that tells applications.
Mm-hmm.
So when you click on it, there is a set of applications, and depending on what you installed, it's different. And if you go to the end of this list, there will be box with that tells folder that tells utilities.
Mm-hmm.
And if you click on the utilities, at the bottom, close to the bottom, will be black box that calls that is terminal.
Okay.
Did you
terminal? Okay, here.
You see it?
Okay.
And then click and open it. And then inside this terminal, type this SSH command. It should work right away. And I'll send you the keyword in the email. And for today, you may skip this -y command, because we are not going to use Gauss view.
So where I'll paste it, like SSH kiln at the top.
In when you open the terminal.
Terminal, how I'll open?
Let me. Do you see what I'm doing? So I'm going to applications, then going to applications, then I'm looking for utilities, and at the bottom of utilities I see terminal.
Where activities I'll go, once previous all those things, where I'll go.
Let me do once again.
Previous
Applications.
Application is in my personal laptop. Where I'll get the application?
At the right bottom. So you have a front panel, right?
Yeah, applications. Okay. Just wait. Okay, I'll help any of my friends. Then
yeah,
next week I'll start.
Okay, but this is quite. If well, I want to help everyone with class materials, but at the end of class we may do the following. If you didn't figure it out yet, you can share your screen, and I will just tell where to go and what to push. So if you want, or we can do a separate session through Skype later.
Yeah.
Okay. I am stopping sharing and sharing again, just different window. Okay, and the goal is to get this figure at the bottom, and the steps are slower. Let us click. Okay, so inside this log file, and I'm repeating what we did before. In the middle of the file, there is a list of molecular orbitals, and I do want to extract them into a separate file. So there is a pre-made script, and I will share it through common chat. So you type the name of the script and then the name of the .log file that you generated with Gaussian. And after that, one provides several parameters. I will tell the meaning of the parameters in a minute. And let me share the line. Okay. And yeah, one needs to type Perl before the script. So after this script has completed, there appears additional 4 files. And these files are results of extracting, of parsing the orbitals from the Gaussian output. So before we go forward, let me, I'm going to browse through directories of class participants and check if you have these files generated. And if I see these files are not there, I will try to help. So yes, of course. Tao, you're welcome to log in, and then you can transfer files. It will be the quickest thing.
Oh, so you mean I can log in that SSH address you provide?
Absolutely. And just let's not discuss by words because it is recorded line. But I'll email you the keyword.
Okay, sure. I will try that. Thank you, Dimitri. Yeah.
My pleasure.
So I tried to copy the command line that you typed in the chat room, but it shows no such file or directory.
I know how to fix it. We'll be with you in 20 seconds.
Thanks.
Tao, I did send you the keyword. So let me know if it doesn't work, if you do not see it in the email. You
Sure. Yeah, I got it. Thank you.
Okay. Yeah. And let me okay. PWD. It would be great so that we have everything organized. If you create a subdirectory for your exercises here in here, right? And you can create subdirectory, right? I'm going to address question of you right now. Which directory should I go to? Lab 10? Yes?
Lab 10.
Okay.
Yes.
Lab 10, okay. ls minus lt start dot log. Okay, so we have this one for G chemical broom.
Not this one, the second one. So not this one, is the energy HF nano 2D broom dot obd. So it's the second one.
Below. Oh, okay. Yes, I see. Here, right?
Yes.
Okay. I will open a new subdirectory. Otherwise, I will get crazy myself. Make directory. Let's call it titanium 1. Copy this stuff into titanium 1. CD titanium 1. Okay. Now I will bring up the command. So I'm pushing the arrow up, and I'm erasing the name of the argument file. And now I will type here the name of the original file in your directory. So the command, first one types Perl, because the script itself is in interpreter. Second, there is this Perl script, then space, and the exact name of the .log file created by your Gaussian calculations. And then 4 parameters that I will explain soon. So I am hitting enter, and everything works. So if you did literally repeat the thing that I was doing, it may not, it may failed. Let me make a little bigger font. I see it is not very visible.
Could you explain what's the command mean, the per, the bin, Gauss gap or something? What that .pl mean?
Yes, I will. So it was question of Professor Tao Yu about sharing the script. Let me show it here. So if I type more in the name of the script, so it reads the .log file and extracts. So it looks for the keywords alpha occupied, alpha unoccupied, and parses them into separate files, and then does a few additional things. So it's the script that does something that we can do by hands, but in a little quicker and elegant way. And if we look onto the output files, and right now I'm sitting in the directory for Yuzhang. So if I type more e underscore OC, it shows everything that was all alpha occupied energies that were originating from the .log file. If I type more e underscore vert, it shows all unoccupied orbitals. Make sense?
So this command is to find the information that we need for occupied or virtual orbital.
Yes, yes. Instead of scrolling through .log file, it extracts this most important thing. But it's not the whole story. It does a few more things. It does a few more things. If I look onto more e underscore whatever it is, it shows the same information but in a little better format. So it shows first column is the number of orbital. Second column is energy of the orbital in electron volts. Third column is energy of orbitals in electron volts, and the fourth column is number of electrons number of electrons on this orbital. So, and if we follow this last column, we see 2, 2, 2, 2, 2, 2, 2, 2, and then 0, 0, 0, 0. So orbital number 24 with minus 12 electron volts has 2 electrons. Orbital number 25 with 1.15 electron volts has 0 electrons. So from this line, we identify that 24 and 25 are HOMO and LUMO. Yeah, Joanna, thank you for joining. Have a nice week. And Joanna, please rush to practice terminal. This is critical. And feel free to disconnect. Yeah, thank you. Okay, so you see from this line that 24 and 25 are HOMO and LUMO. Okay, so now
yes.
It's not the whole story. There is one more file. Let me do s-ot, which is called DOS. And I'm going to explain about it, but before, let me browse through directories and see that Kristen was successful in doing this exercise. Oh, let me pwd so that I know where to. Okay, yeah. Thank you, Tao, for making directory for yourself. I'll help you, Christine, and then visit your directory if you want me to. Okay.
Yeah, sure. Yeah.
Okay. So, Kristen, I'm going to lecture 12. SOT.
I think that I was able to participate in lecture 10 subject, but I not be able to
Something I see that length of the virtual and occupied orbitals is 0. This is not right.
Yeah.
Let me quickly.
So
Yeah, I'm listening.
I repeated it in lecture 10, and I think it's working there.
Oh, now you're working in lecture 10?
Yeah, I just tried, since my originally when I copied from lecture 10 to lecture 12,
okay.
There were some error messages, but...
Okay, yeah, not a problem. Lecture 10. LS minus OT. Better. Let me look for more EOC. Yes. More E underscore virg. I'm always typing things wrongly. MORE. Okay. Okay. Homo 24, Womo 25. Very good. So, Christine, you are on the same page as everyone, and I will visit the directory of Professor Tao Yu and check if things are going well there. Those are cool. Oh, okay. Nice minus OT. Text. No. Let me open another directory so that it will be empty. It will be 12.
Sure, please. Yeah.
12. CD 12.
Oh, it's the file.
It was lab 6 in regular semester when we had labs once per week. Now we have it twice per week, so and we make them shorter. In semester they're 3 hours long.
I see.
So copy. One can run Gaussian, but it will be just quicker to take output file. Lab 12. So I'm copying .log file. So it's single point artifact for a very small molecule. And now,
sure.
And now I'm because I'm lazy, I will not type it over. I will just do arrow up until I find the right thing.
Okay. Yeah.
And now typing the name of the .log file.
Sure.
And then hit enter. ls minus lt. Minus lt. And now it has these files, and they are not empty. More e.
Okay. Okay. Here we go. Yeah.
Okay. Good.
Thank you. Thank you, Dimitri. Yeah.
Oh, my pleasure. My pleasure. So, what is the meaning of these 4 parameters? Let me go 1 page forward, and because I'm sharing screen, everything happens with a little delay. Okay, and I will increase it bigger. Okay. So the let's analyze what is on the figure and then go over the practical steps. If we look into the list of orbitals, then the LUMO is near 0 electron volts, and HOMO is near minus 12 electron volts. For these calculations, I'm not telling that in the nature, in reality, it will be the same values for this molecule. But so now, if I want to see several more orbitals, not only HOMO and LUMO in this visualization, I am selecting an interval. So about 5 electron volts above LUMO and about 5 electron volts below HOMO. So those are, let me bring the command line. I'm bringing the command line and typing. Yes. So the last fives here, there are 4 arguments: 1000, 0.0155. So the last 2 numbers, 5 and 5, they are telling how many electron volts below HOMO and how many electron volts above LUMO. So in this DOS diagram, we are showing area of the band gap and plus and minus 5 below and below HOMO and above LUMO. If for your personal reason, for your research reason, you need maybe you have a metal with 0 gap and you want to focus only on the gap area, you can put 1 and 1, and it will be much narrower interval. Maybe if you deal like if Dr. Yu Zheng, if you deal with infrared emitter with band gap around 1 electron volt, and you do not care what is happening at plus and minus 5, so you would put like last numbers 1 and 1 to show gap area and plus minus 1 electron volt. So the next parameter, 0.01 in here. So this parameter tells what is the width. So if one increases this image, one will see that each individual orbital energy is represented by very narrow, tiny Gaussian. And right now they look like straight lines because we put very small width of the order of 0.01 eV. But one can do, Tao, I will do it in your directory, later you can correct it, if you don't mind. So one can put the parameter instead of 0.01 a little bigger. So and then later on, when we will create the image like this, it will be more continuous. And the first parameter among these 4, 1000, it is a number of grid points. So the overall density of states is represented as set of discrete points that show this line. So the number of 1000 is how many grid points are used there. Okay? So I did just little interpretation, but we need to go forward into fabricating such image. So let me bring instructions here, and I will go to my directory so that I do not create stuff in other directories. So I'm going to lab 10. So not 10, sorry. CD lab 12. Okay. So Next step is just for practical reasons. I'm going to copy. Oh, let me show. There is one more file that starts with DOS. More DOS and whatever after this. So this file actually does have everything we need. So it has lines corresponding to grid points and value of this line. And if you download this file and plot it with Excel or Origin, you'll have what we need. I'm just trying to avoid Microsoft products when possible and do things in the command line because for high throughput production it can be useful. So for this purpose, I am making a copy of this DOS file. Copy DOS blah 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 into more standard name dos.log. So it doesn't change the file. And now there is a script that converts this list of data into graphical file. First into PostScript, which is very ancient, and then converting into PDF. So I'm typing GNU plot tilde bin GNU prog underscore dos goes. So if you are curious what this script is, it's just a list of parameters for a standard GNU prog program. So it's replacement of Origin or Excel, and it just tells plot this file using first column as X and second column as Y. So it's nothing else. And after this command has been done, I'm doing ls-lt, and there is a file named dos_go9.ps. So it's not forbidden to look inside this file, and there is a software that allows to watch graphics in this format, but it's a little obsolete, so it's better to convert this PostScript into more standard PDF. If you look inside it, it shows some text which shows at which place to put the point or little line. So if I type PostScript PS to PDF right, and then give the name dos_go9.ps ls-lt, it does create the PDF file. And now I do want to download this file from the Photon server to the local computer. Because it's better to run graphical applications on local computer. So I'm copying the path, edit, copy, and just in case I do things too long, I put TOP to prevent log out for lack of activity. Now I'm going into another directory. Here I can exit from Photon, and now I'm doing on my local. Now here I'm on the local computer, and I'm doing scp user add name of the server, column, path, and then I will copy everything that ends with the extension PDF space period here. And then, wait, I probably mistyped things. Let's make, yes, it is double M in the name. Okay. Now typing the keyword. And just I will copy this line to everyone, but please use your own path to your directories because it will be more interesting to see your results. Okay, and now on the local computer, I do see this DOS_Go9 PDF, and I may want to open the PDF reader like Acrobat and browse through the directories and open the file. Things too long, but I hope everything is fine and it will. Yes, it pops up. So this generating of such image is the goal for everyone, and I will go to directories and see if you have this this file. Before, let me do a little experiment and show it to everyone. If I do the same if I quickly repeat the same operations with different width, so I'll take maybe even bigger width, like for illustration. And if I do it, I need to replace okay. If I'm doing it once over again with different width, you see the width parameter is encoded into file name, and now I'm copying it into the generic name. Which is being read by GNU Plot. And I'm running this GNU Plot once again. PS to PDF write DOS G09 PS, and let me copy CP DOS G09 PDF just modified W. Space. PDF. Okay. P and repeating the download command. And now I can see what is the consequence of using 15 times bigger width. So now it looks more continuous. So several lines are combined into bands, and it deals with that solid state scientists called, instead of telling occupied and unoccupied orbitals, they call it conduction band for unoccupied and valence band for occupied. And in this small model with so few orbitals, these bands are composed of very few lines. But if we will take much bigger models with more orbitals, this continuous representation will become much more reasonable and useful. And this is just one, the model is one titanium and 4 hydroxides. Let me browse through directories and check if everyone was able to get through this point. Oh, I should look not in here, I should be here on the photo. So I'm in the directory by Christine. Okay, I do see you have a PDF file. Were you able to download, Christine, were you able to watch this file? Were you satisfied with its visual appearance? Please.
Onto my local computer.
Pardon?
For some reason, I can't copy it to my local computer.
You should. Let's do it together as a task number 1. So PWD. Okay, and if you share your screen, we will be able to do it with guarantee. I have no doubts. Okay, let me see. SCP user photon cam this unit. Okay, use scratch cam lecture PDF. Ooh, can you type PWD right in this window? But you okay, you are in this window. You are on the photon. So please copy your previous command and go into the tab on the local computer. Open maybe new tab or just click into different tab. Okay, space, wait, arrow up. Same thing, space, period, and then enter. And then the keyword. And can you open it and see if it matches your expectations? It was already showing it. Let's go back to the terminal window. Please type pwd. Oh, it's in OneDrive. Yeah, this one. Okay, yeah. I don't know about you, but it matches my expectations. I'm happy with it. And for having more continuous, you may use bigger parameter for the width. Okay, let me look for other directories, other participants. Which directory should I go? Titanium 1 or Titanium 04?
04H4.
Okay. So you do not have this. Oh no, you do. Okay. Did you download it to the local computer and watch it in Acro?
Yes, I opened it.
Does it match your expectations?
Number is correct. I can show you the screen.
Yeah. Yes, please. Would be great.
Okay. Sorry, now I use Firefox. I don't know how to.
Oh, okay. You can send me a file by an email. I will watch it. But if you think if it is okay, then it's fine. So if you are interested to do homeworks, you may try to do this Gaussian single point calculations for few models that we considered in class, specifically for those that are interesting for you. For oh yeah, Tao. Thank you for joining. See you soon. Yep. And we have a meeting tomorrow, I believe, at 2. The models with functionalized flake and for carbon small fraction of carbon nanotube that we generated, you may run single point with Gaussian and see and look on density of states for them.
Okay.
So it will be a really good bridge to your professional interests, and we may do a cooperative project with a real calculational project later, and you'll have hands-on experience how density of states for these objects, and I think it will be really great.
Okay. Okay, great. Thank you.
Yep, thank you. So I think we are done with today's program. If there are more questions, I will be happy to answer.
Can I ask a question regarding the presentations?
Okay, let me bring up the list because I don't remember it from the top of the head. Okay. So
So my question is actually not based on the content. It's just I realized the date is Monday the 13th.
uh-huh. Are you superstitious? You're superstitious and you do not like the date of 13?
No, that's fun. It's just my sister is getting married that weekend before, and so I'll be out of town. So I was wondering if you'd like me to present early, or I can have a recording.
No, if it is so important for you, we can just postpone it to Wednesday. But recording earlier is not ideal because it will be before all materials are presented, and recording is not ideal because you will not be able to stand the questions which may or may not appear. So the live answering questions, I think it is better. So if it is a real challenge for you to present on Monday 13, I will seriously consider to move the whole group to Wednesday 15th.
I really apologize for this. My sister's wedding is in Arizona, so I will be unavailable completely throughout Monday due to travel.
Okay, so there will be no online connection.
Unfortunately.
Okay. Yeah, thank you for giving me the options about, and I'll think about it and match your plans. And you may start preparing slides. Well, maybe start preparing them next week. This weekend I will send templates and examples, and then you prepare and share with me, and I will just update on exact plans so that everyone will be happy.
Okay, thank you so much.
Oh, not a problem, not a problem. Anything else we need to discuss? If no, let me suggest that we disconnect. Do you approve it? Okay, then I'm closing the session. Thank you.